We will have Manu, Sridharan with us talking about challenges in large-scale mobile app performance. And please welcome.
All right, thank you. Can everyone hear me? I'm getting over a bit of a cough, so I'm not going to speak maybe as loudly as I usually do. But if everyone can hear me, then we're fine. All right, I'm really happy to be here. Today I'm going to talk about some challenges that Uber faces in mobile app performance at the large scale and some of the tools that we're working on to try to address these challenges. So as some brief background, Uber builds apps. I don't think anyone will be too surprised about this. You might be surprised by the number of apps that we're working on. So you're probably most familiar with the Rider app for booking rides. We also have a separate app for drivers. And then more and more apps are coming out. This is Uber Eats. We have Uber Freight for shipping freight. There's a new Uber Lite app for developing regions. And beyond the number of apps, in each of these apps, we're constantly shipping new features on a weekly basis, right? So even though it's the same app, there's a huge amount of churn in the code base constantly. So in this scenario, one of the big challenges is maintaining app performance because it's really, really important. So what are the metrics that we look at when we're talking about performance? There's actually a number of different things that we care about. So binary size, how big is the app when you download and install it on your phone? How long does it take to start the app? How responsive is it as you're performing interactions? What's the impact on battery life as you're using the app over an extended period of time? There's a lot of different things that we measure. And maintaining good performance is really key just to the fundamental usability of a mobile app. We're not talking about, oh, this feels a little bit slow. It sort of feels broken, right? When you're operating with an app on a touch screen and you start operating on it and it's not responding in an almost immediate fashion, it just doesn't match with the experience that people expect on a smartphone. And beyond just using the app, it's pretty key to being able to install it. And for some of our users, like delivery couriers, they might actually be using the driver app for an extended period of time just on battery. So in those kind of scenarios, the battery usage is also hugely important. And this has been measured. So when we regress on performance metrics, it's correlated with regressions in important business metrics, like installation rates, like whether someone who installs the app actually successfully takes a ride. You've measured that these performance metrics actually impact those bottom line metrics. So we know this is important for the business. So I mentioned challenges in my title. So what are some of the challenges that we face? So one of the biggest ones is just a huge variety of devices out there that we're shipping our apps to. This is a picture of what I would characterize as a very small Android device lab. In reality, there are hundreds of device models that are running our apps on a weekly basis with huge variance in hardware characteristics, right? And not just things you might think of like CPU and RAM, but it turns out that the quality of the flash storage varies hugely across Android devices, and this can turn into a huge performance bottleneck. Say if you're doing some I/O but not doing it on a background thread, that can actually have a very detrimental impact on app performance on low-end devices as well. So beyond the hardware, there's actually enormous difference in the compilers and the garbage collectors on Android. And this is because there's so many different versions of Android that our users are using, right? So in terms of compilers, if you look at the evolution, first there was Dalvik, which evolved to have a trace-based JIT compiler. And then Dalvik was replaced with ART, the Android runtime, which before Android 7.0 primarily used ahead-of-time compilation for your code. But now, post-Android 7.0, it's using both ahead-of-time compilation and a JIT compiler. So you can imagine how just even reasoning about what a change in your code does in terms of performance in the field is actually quite difficult with this situation. So beyond device variety, There's a bunch of other challenges. I don't have time to go into extreme detail on them, but we're dealing with a huge variety of network conditions. Sometimes your network is just really slow, and we don't want the apps to unnecessarily slow down in these situations. Our application code makes use of several complex third-party libraries and frameworks. So frameworks like Dagger for dependency injection on Android. This is Dagger 2, actually, and under the hood, it generates a lot of code, which can execute at unexpected times, or you just might not understand the full cost of the code you're writing because you don't see it. Similarly, we make heavy use of the ReactiveX frameworks for functional reactive programming in our apps, both in Java and Swift. These are, again, complex frameworks where you might not understand the performance cost of something that you're doing. And finally, it can be really hard, as I mentioned before, to even measure the impact of the changes that you make. Beyond the huge device variety, it can be quite noisy just to measure the running times on a single device, like a single mobile phone. I think this is well known, has been studied more in the desktop or server scenarios in the academic community when you have managed runtimes, just the amount of noise that you get across runs, how difficult it is to measure the warm-up time. So I think this is actually compounded on a mobile device just because it's even harder to control some of the aspects that can introduce this noise. So with all these challenges, what's our approach? Is the slide flipping here? There we go. Well, it's a multi-pronged approach to dealing with app performance, and it goes well beyond my team. We have a whole mobile performance team, too, that does a ton of great work in this area. So one important thing is measurement, obviously, right? So we do instrumentation of our apps before we ship them of certain important spans that we want to run fast. We collect a ton of analytics from the field, and based on that, build dashboards and have alerting for any serious regressions in the field. If say startup time regresses by a lot, someone's going to get alerted by that and has to investigate. So when you have a problem, how do you figure out what's going on? One important part is profiling. And here it's really critical that our profilers have low overhead, low perturbation, because as I mentioned, just even without profiling, there's already so much noise that if your profiler is introducing a huge amount of perturbation to your execution, it's almost useless in terms of actually trying to reason about what's going to go on when you're not running the profiler. Then unsurprisingly, we're doing work on optimization, both compiler optimization and it's quite important to do manual optimization of the core libraries used by our apps, again, based on the profiling data. And more, we're looking at prevention, trying to catch regressions in performance very early and prevent them from ever shipping. So this can be done using regression testing, trying to automatically measure the impact of changes as they go into the code base. But we've also been looking more at using types and type inference to catch well-known classes of performance problems and just catch them at compile time even. So in today's talk, I'm going to focus on, well, it looks like green on my screen, but sort of the darker areas on this slide, and just cover a couple of different topics that my team is focused on within this big space of work. But before I get into the technical details, I just wanted to talk about at least the philosophy of my team. We're a team of people with research backgrounds. So how do we try to work in these projects to have maximum impact? So one thing that we do is we try to work very closely with developers, not just the folks on the performance team, but the actual people building features in the apps. And this is very useful, one, because we can try to influence the design of frameworks moving forward to avoid problems with performance that we've observed in the past. And also, if we get buy-in from developers, then we can convince them that it's worthwhile to write certain annotations in the code, which can make things like static checking much, much easier. We're also very open to trying to do custom optimizations for our own code patterns, right? So I mentioned compilers, and typically you imagine a compiler optimization as just you put it in, and it's able to run on any code in that language. But we're also definitely investigating just maybe source-to-source optimizations that catch patterns in our code base and optimize those if they're really important for our apps. And finally, we're very interested in open source. We've released open source tools. We upstream things to other projects. We really want to bring the community along with whatever tooling we build in this space, and let teams from other companies and academics leverage the stuff that we've done so that people aren't constantly reinventing the wheel. So with that, let me go into the first kind of technical topic, which is around profiling for our Android apps. And one way that we got into this work, or actually probably the main way, is I saw this great talk at the AtScale conference in 2017. It's called Scaling Android with Redux. The talk was given by Shane Ney from Facebook. And Redux is a tool that Facebook has built and open sourced for doing basically bytecode to bytecode optimization for Android apps. And this talk specifically focused on a particular optimization that they did around code layout. So they would instrument the app, see what order classes were getting loaded, and try to reorganize the desks files so that when those classes were get loaded, the I/O would be more sequential. So this would reduce things like the number of page faults that happened at app startup, and this would actually, they showed amazing measurements, like huge impacts in performance on certain devices due to this optimization, particularly devices running older versions of Android. So we gave this a shot, but when we ran this on our apps, we saw much less improvement than what I had seen mentioned in this talk. And so the key question we want to understand was why? What exactly was going on in class loading in our apps? Where was the time going? And why were we not seeing so much improvement from this tool? So the natural thing to do here is to try to run a profiler. But we found that existing profilers on Android had limitations that made it really hard to understand what was going on here. So when you're trying to understand execution time, in a typical profiler, there's a couple of different approaches. One is tracing, where you kind of instrument, say, every method enter and exit, and you have collected a very detailed information about how much time is spent in each method. And the opposite approach, if that's too high overhead, is to do sampling, where periodically you just look at the stacks of all the threads and aggregate this information to get a picture of performance. So there is a sampling-based profiler that comes with Android Studio, but we found that the information it gave was too coarse. And this kind of ties in with the story about having a huge variety of devices. Okay, so our developers are often using higher-end devices when they're trying to profile our app. And on a higher-end device, something like tapping a button and getting the response might run very quickly, on the order of a couple hundred milliseconds. But that same interaction on a low-end device could stretch to a couple of seconds, right? What we'd really like to do is to be able to do our profiling on this high-end device, but collect very detailed data so that we can try to fix performance problems without having to directly do all our development and profiling on those low-end devices. So you might want to get very detailed information for what seems like a short span, since that might run much longer on a low-end device. So this is the reason that even though sampling will often work, it was too coarse for our use cases. And finally, the profiler was missing some low-level metrics that we were really interested in. For example, a detailed breakdown of the time spent during class loading, which was important for understanding the effects of this particular optimization. So the performance team, the mobile performance team, has open sourced this tool called Nanoscope. And the key feature that it shipped with was very low overhead tracing-based profiling. So I can just show you, they built this cool animation that shows you Nanoscope on the left with profiling enabled for a particular tap versus the default tracing profiler. So as you can see, Nanoscope has much, much lower overhead. And how did they do it? It's not too surprising. Basically, they hacked the Android runtime. They hacked the interpreter and they hacked the JIT so that they inject very low overhead code at method entry and exit to collect these traces very efficiently. I don't have time to get into all the technical details here. There's a nice blog post on the Uber engineering blog if you want to see exactly how this was done. So there's a downside to this, which is that once you start hacking the Android code, now in order to actually use the profiler, you need to build a custom ROM and have it run either in a simulator or on an actual device. And we don't support every device out there, but for us, we have devices that we can run this tool on, and we can get really great information out of it with very low overhead. So coming back to the class loading issue, our team saw that Nanoscope could actually be a great platform for us to collect all kinds of other metrics about what's potentially affecting performance on the app. So we've added detailed class loading metrics to Nanoscope. So you can get information about how much time was spent doing I/O during class loading, or how much time was spent specifically doing bytecode verification. And doing some initial investigation, we already had some interesting find. For example, this auto-value JSON library was forcing some eager initialization, which ended up leading to hundreds or thousands of classes getting loaded during startup for our app that didn't need to be. So that was fixed with a pull request to that library, and that got us a nice win in terms of startup performance. We were also, for one of our frameworks, basically generating an enum, a Java enum, with hundreds of constants. And the problem with this is that when that static initializer runs, it's going to actually be quite expensive just to initialize all the fields for that enum constant. And you don't have much flexibility using a Java enum to delay this initialization and do it lazily if you want to. So working with the developers, they're redesigning this framework, and they're going to take a different approach. Rather than generating an enum, they're going to generate efficient code so that they can do more lazily initialization of this data structure, and it doesn't have to run on the main thread during startup. And there's much more work to be done here. We're still understanding the interactions between class loading and multi-threading, and I expect we're going to get a lot more wins here as we dig in further. So that hints at our plan, right? We want to expose many more metrics to developers via Nanoscope, things like CPU utilization of threads, or how many page faults are occurring, low overhead profiling of allocation, lock contention. There's tons of stuff I think that can be done, and we're sticking this all directly inside Nanoscope, trying to develop it as much as possible in the open. And I think this could turn out to be a great platform for everybody, academics, other companies, to try to build a really, really rich profiling tool for Android. So we welcome you to join in on this effort. OK, so I've talked about Android. Let's switch over to iOS. And here, Uber made a huge bet on Swift early on. So right now, our entire rider app is written in Swift. Our new driver app is written in Swift. And so we're huge consumers of Swift, and we need it to be optimized well. And my team has started to dig into the kind of optimizations that the Swift compiler is doing, and we're seeing some opportunities for improvement. So the case that I'm going to focus on today is around the usage of protocols in Swift. So let me give you a sort of very brief introduction to how these look, but they're kind of like Java interfaces, if you're familiar with those. So you can have a protocol like this one, which just defines a function getVal that returns an integer. And then you can have a class conform to this protocol, and that means it has to provide an implementation of this function. So this is a very simple implementation that returns 10. And then you can write code that has a variable which declares the type, whose declared type is the protocol, and you can invoke the method that's declared in that protocol. Nothing too surprising. So what's interesting for us is that if you look at the design of our rider and driver apps, it's very protocol heavy. So I think it's in our rider app, we have more than 5,000 protocols in that app. And the main reason for this is for testability and mocking. So for a lot of key data structures, we have a convention where you always define it as a protocol. so that you can create a mock version of that protocol when we're doing testing, and then have a real class corresponding to that protocol for production, right? So protocols are used very heavily, and one thing we discovered is that if you look at this final call, x.getVal, it's quite obvious looking at this code that even though this is invoked via a protocol, the implementation type is some class, and you know exactly what function is getting invoked here. But the Swift compiler is not able to devirtualize this call. And this is really important because this devirtualization is really critical for other optimizations like inlining. And so a lot of performance is getting lost due to lack of effective optimization of these kind of code patterns, particularly for our app, which is so protocol heavy. So the optimization that we've been looking at is around removal of existentials. So where did this word existential come up? Well, with Swift, when you compile it, before it gets reduced to LLVMIR, it first gets reduced to SIL, the Swift intermediate language, and a bunch of optimization happens at that level. So what you see as protocols at the Swift language level in SIL are known as existential types, which matches up with the standard definition of existential in the type system literature. So what we're currently working on is enabling devirtualization of these so-called witness method calls that happen for existential types. And in the future, we want to push further to have the optimizer basically entirely remove existentials from the code, including all the corresponding data structures if they're not being used anymore. So how do we do this devirtualization? It's not too surprising, via a concrete type analysis. So down here, we want to be able to show that the type of X is always this type sum class. And if you know that, then you know what this getVal call is actually invoking. So this looks just completely trivial at the source level. At the SIL level, it's a slightly trickier. So I can show you, I'm calling this pseudo-SIL because I've elided a lot of details here. But this is how these last two lines of code look like in SIL. So you store a reference to this sum class constructor, which I didn't show. But v1 is holding the sum class object that gets allocated here. But then when we assign it here, this init existential ref instruction is there. This is essentially doing a boxing of that reference. So this creates a box that has a pointer to the original sum class object, but also a pointer to what I think is called like a value witness table. It's a dispatch table that basically, if you pass this thing around, tells other code how to invoke functions like getVal, right? Because it can be different for different types potentially that conform to this protocol. So when we actually do the invocation, we have to do a corresponding open existential ref instruction to unbox this, this pointer, and then finally we do this witness method invocation. So given code that looks like this, how can we do this concrete type analysis? Well, the first approach is to do a data flow analysis, accounting for this boxing of existentials, right? So we want to know what is the concrete type of v3. We have to track the data flow through this unboxing and boxing operation back to this reference to sum class. A second, simpler approach, which actually works pretty often for our app, is to just look at the type hierarchy and also the visibility of these types. So if in a particular module you see that there's only one class conforming to a protocol, and if that protocol isn't public, so it can't be implemented by other modules, then you just know everywhere that protocol is being used, there's only one possible class. So that's an alternate approach that does work in many cases. So we have an implementation. We built this concrete type analysis. We're using it to devirtualize calls. There are some inter-procedural cases. I showed you those boxing instructions for existentials. So sometime the open existential ref instruction is in a callee, and the init instruction is in a caller. So to avoid doing some very expensive inter-procedural analysis, we do some targeted inlining. We also leverage some existing specialization that's already there in the Swift compiler. But when we implemented this, we saw some very promising results. Thus far, we're seeing something like a 5 to 8% speed up in app startup time. And I mean, to get that for free via compiler optimization is just awesome, right? Because developers don't have to do anything. You just run the new version of the compiler, you get this nice performance win. So what's work in progress is we're working on upstreaming these changes to Apple, to the Swift compiler, so that everyone gets the wins. We've already upstreamed some changes around tunability of this O size parameter. So we care a lot about code size too, and we've upstreamed some changes to them so that you can tune how the code size optimization works. And we're working on upstreaming this too. So, fingers crossed. Hopefully, in the next major Swift release, everyone will be getting better optimization of protocols via these changes. Okay, so one last topic I want to cover is around both checking of reactive Xcode and also some preliminary work we're doing on trying to optimize reactive Xcode patterns. So what is reactive X? Well, a very brief and oversimplifying definition might be it's a streaming abstraction that can be used across both synchronous and asynchronous inputs, data sources, all kinds of things. But let's make it concrete. Here's a very simple example where, let's say, we're trying to get a feed of cars from some server. You might have a function that gets that and returns it as one of these observable streams. And then we can take that stream, and whenever an actual value comes back, we can run a filter operation. Let's say, we only want cars that don't have a passenger. And then this looks like Java 8 stream type code, right? You can do a filter, then a map to get the location. And then at the end, you have a subscription where, say, here we're displaying the car on a map, or if you have an error, render the error message. But this is the basic idea. It's like Java 8 streams, and they're used all over our code bases, again, to abstract all kinds of inputs or even communication between different models, kind of standard subject-observer patterns. It's nice because it's uniform. Once you learn it, you can use it for lots of different things. But there are some gotchas when it comes to performance, particularly when Rx interacts with networking. So here's one example, a bit contrived, I'll admit. So let's say we're getting some car information from disk, and that's abstracted as an observable. We're getting information about friends from the server, and now we want to combine these somehow. Don't ask me why. Maybe you want to put your friends' pictures on different cars, but this combine latest operation will basically take each pair of values coming in and let you operate on them. So what's the problem here? The problem is that this friends from server call may return an observable that's very slow to emit, right? Because we're waiting on the server. And if you have a bad network connection, it might take a long time. And this trickles down because this combine latest operator is going to wait for all of its inputs to emit one value before it does anything. Okay? So if you've combined a bunch of streams together and you're not aware that one of them is hitting the network connection, you can be surprised when something just completely stalls in your app, and it's because this combine latest operator is waiting on that network operation. So at the code level, there's a number of different fixes for this. You can provide a default value for the network observable or do a timeout. So here's another gotcha. Let's say we're getting the phone location from the local device, and then, I don't know, getting its altitude out and logging that to the server for some reason. The problem here is that this phone location on the device might be updating very frequently. Like, let's say it's updating every 50 milliseconds. This means that every 50 milliseconds, I'm sending out a network request to the server. And this is potentially horrible, right? On a low-end connection, this might just be completely clogging the network connection. So if you have too many network requests, this can hurt performance. And there are solutions here around, like, say, throttling or using a distinct until changed operator. So we've got these two different kinds of issues. How can we try to address them? Well, we've had this idea about trying to check all kinds of properties of these observables with refinement types. So let me just walk you through how this works. So we want to be able to refine this observable type for the property of interest. So an example might be you might add this network annotation to any observable that's actually emitting values that are sourced from a network connection. Okay? So now, once you have this property, we're going to need some type annotations for the core library methods. So for this friends from server function before, you might need to annotate that as saying, oh, this is returning a network observable. And then we need to annotate the core operations within the observable type. And this turns out to be pretty easy because most of the operators don't do anything to your property. So you can just use parametric polymorphism and say whatever observable type comes in, T1, that's the type of the result observable. Now that you have these types, we can use type inference to check your code for errors based on properties we defined. And we can leverage frameworks like the Checker framework from University of Washington to do this. So for the examples I gave, you might want to say, OK, don't pass a networking observable to combine latest. Or you might want to say, if you have a subscription to an observable that's emitting frequently, then don't do a network call from that subscription. So it turns out we've actually already built out this framework, and we're using it not for performance right now, but for correctness. We have this shipped that we're checking UI off main thread bugs using this kind of approach. And we have a paper that's going to appear in ASE 2018 on what we're doing in this space. So let me walk you through how this would work for one of my examples. So this is the one with the phone location that was emitting too frequently. So in this approach, we'd say, OK, now we're going to annotate this as returning a frequent observable. And now we have this map operation, which also, since it doesn't change anything, also returns a frequent observable. And we're going to have to know that send to server has some kind of network effect, right? That it's communicating with the network. And we can report an error here, saying, hey, this is emitting frequently, and you're sending something to the network for each value. So for a fix, if you added this throttle call saying only emit every 2 seconds, we could add an annotation that says, OK, throttle takes a frequent observable and makes it infrequent. So now we're fine, right? Because we fixed the problem with the frequent network requests. So I'm running a bit short on time, but I'm going to briefly walk you through one other optimization project that we're working on around kind of unnecessarily bloated RX code. So let's say we have this method to resize an image, OK? And we decided initially that, OK, maybe this is expensive, so we might want to do it on a background thread. So rather than just returning the image directly, we're going to return an observable that emits whenever this operation is done. And finally, when we get the resized image, we're just going to subscribe and write it to a field. Okay? But maybe after further exploration, we found that it's not worthwhile to stick this resizing operation on a background thread. So in this function, all we're doing is calling the scale function and then just wrapping it in an observable directly. So now we see that we have this sort of boxing of the image in an observable for no good reason. So we'd like to be able to take this code and optimize it so it just looks like this. Just a field write of the final scale image call and without all the observable overhead. So we have an intern who's working on this in the context of Swift. And we'll see how well it works. It's still a work in progress. So briefly, before I conclude, I wanted to mention that this has been very app-centric, but we're starting to think about doing work that goes beyond the apps, because there's a lot of other code running at Uber that we could use these kind of technologies for. So in terms of developer productivity, we'd like to speed up parallel builds, right? We have these nice build systems that'll build modules concurrently, but we think there's opportunities to improve the job scheduling that these build systems are doing, trying to lint for bad practices. Right. We'd like to do more profiling for back-end services. So Milind Chubby, who just joined my group, has done some really great work around lightweight profiling, including this Witch tool, which was described at ASPLOS 2018. We think there's a lot of potential for finding performance bottlenecks there. And also more forward-looking, but there's this Pyro project for probabilistic programming out of the Uber AI labs. And we think there's a lot of potential to accelerate execution of those programs. Right now, they're using PyTorch, but we might be able to go directly to LLVM and speed up those programs a lot. So that's it. To conclude, we've got a variety of performance efforts going on. And generally speaking, we like to work closely with developers and open source our tools. So thanks a lot for listening. I'm happy to take questions at this point. Thank you. Yeah, are you going to walk around with the mic? Sure. Question right there.
You had the example of submitting network requests too frequently,
Right.
and how you use the types to say what is frequent and what isn't. Is it possible to have like a compiler option to say how many requests per second is considered frequent, and then if so, like when someone has a call to throttle, can you actually check the value of the throttle parameter to see if that matches the compiler option for what's the threshold?
Yeah, I think that should be very possible. It's going to depend on what exactly is getting passed to throttle, right? So we're starting to get into the realm of dependent types. If it's an integer constant, no problem. If it's some variable whose value gets computed somewhere else, that's where probably it may not be worth it to do a very sophisticated analysis to figure out what's passed there. But yeah, it should be easily configurable even as an option that we can tweak outside the checker. Yeah. Sure, question over here.
So I was just wondering, there was this thing about the type refinements. Which language was it? Was it Scala or Swift or?
No, this is just Java.
Java.
Yeah,
Okay.
but it's.
I'm surprised that you can do that in Java.
Yeah, so Java has a very flexible system for defining custom annotations on any type. Now,
so it isn't a part of the type system actually, or is it?
it's not part of the type system.
Okay.
It's metadata that gets stored automatically for you on the AST, but it's up to you to build the type checker and the type
okay.
inference.
Thank you.
Yeah, but everything's in place for you to plug that right into the compiler. Yeah, question right there.
Hi. Do you, since you mentioned profiling on Android, do you have do you find similar problems profiling iOS?
Yeah, I think that there will be some similar problems. One thing is that on iOS, you don't have a just-in-time compiler, so that can reduce a lot of the noise in the measurements, like sort of more the traditional profilers that are there give more actionable feedback even on short spans. And then you don't have a garbage collector also, which doesn't mean that there can't be issues with memory management because there's automated reference counting and sometimes there's too many ref count increments and decrements, but it's still, even that is a little bit more manageable. But that said, yeah, we could definitely probably use some of these lower level metrics on iOS, and it's something we should investigate.
Okay, but the tooling currently is adequate for your use case, right?
The tooling that we're working on right now is specific to Android. We haven't started working on anything specific to iOS yet.
Okay, great.
Okay, I think that's it for questions now. I just want to say briefly something about the lunch. Maybe you've experienced some difficulties yesterday. So when you go up to the restaurant has a limited capacity of 200 seats. So when they're full, they're just going to send people down here. So you can either wait a little bit until they open the buffet here, or they might let people in when people leave after the 200 limit, but it's better to go up. If they send you down, just go down. And it's the same food, so no differences. Let's thank our speaker again and then leave for lunch.